So we're going to take our picture of our galvanic cell and we're going to convert it to a shorthand style view of the process. So I'm going to leave this on the board. I'm just going to scoot this board up a little bit. We can bring it back down if we need to. And we're going to draw the shorthand version of what was in that diagram, with zinc oxidizing on the left-hand side, copper reducing on the right-hand side. Okay. This is referred to as a line notation. For electrochemical cells. The line notation allows us to describe the cell without drawing the picture. But it requires us to know those conventions. Oxidation is on the left, reduction is on the right. Electrons move from left to right. We have to know those conventions so that we get the cell set up correctly in our line notation. So anode on left, cathode on right. So now we're going to write out the picture in word form. So what was happening on the left half cell was zinc was being oxidized. And we're going to write it in that order in our line notation. So Zn as a solid was oxidized to Zn2+. Now there's a phase boundary here because the zinc is a solid going to zinc aqueous. The phase boundary is a single vertical line. So Zn as a solid in equilibrium with Zn2+ aqueous. This is the left half of the cell. Zinc oxidized to zinc 2+. Then we go to the other half cell. We can't just put a single vertical line because there's more than just a phase boundary there. There's a salt bridge. The salt bridge is two vertical lines. The salt bridge separates the half cells. So zinc goes to zinc 2+ on the anode or negative or oxidation side. And then on this side, Cu2+ is reduced to Cu as a solid. So we put a vertical bar again between the copper 2+ and the copper as a solid. So on the right-hand part, after the salt bridge, we're showing copper 2+ reducing to copper. So it's important to show them in this order. Not only oxidation on the left, reduction on the right, but how we write them on each side of the half cell. Zinc is oxidized to zinc 2+ as copper 2+ is reduced to copper. We can watch the electrons move through this. The electrons move from zinc, create zinc 2+, copper 2+ picks them up and forms copper as a solid. So this is the line notation for this picture. Much faster to write. Okay? So some other things that you'll see in these line diagrams. This sort of diagram is one of the easier ones because there were paddle electrodes. We don't always have paddle electrodes like these that were in our picture. Sometimes we have a redox process that occurs in aqueous solution. Iron 3+ going to iron 2+. There's no solid iron there. So you can't use a solid iron electrode. So in those cases, you will sometimes see like a platinum wire shown as part of your diagram. So let's say that we had a reaction like this one. Cobalt, CO as a solid, plus Fe3+ aqueous. So solid cobalt plus iron 3 in equilibrium with CO2+ plus Fe2+. So everything is aqueous on the iron part. The iron half reaction isn't going to have any solid iron anywhere. So when we draw this line diagram, we have to find out what's getting oxidized. The cobalt's getting oxidized. It goes from 0 as an element to 2 plus. So CO as a solid, and then a phase boundary to CO2 plus, aqueous. And then our salt bridge. Now we have 2 ions. We don't have a solid involved on the right-hand side of our diagram. So we separate our 2 ions with a comma. Fe3 plus, aqueous, comma, Fe2 plus, aqueous. Now there has to be something to carry the electricity. There has to be a solid there, it's just not solid iron. So you'll see things like PT is a solid for platinum wire or gold wire or silver wire, something that will conduct electricity really nicely without participating in the reaction. Platinum is the one we use most often for these. So this half cell over here doesn't look that much different than we had before, but this one does. And what's happening in this half cell is, if we diagram just that half cell real quick, platinum wire is sticking down in a solution of Fe3 plus and Fe2 plus. And the way we kind of model this or envision it is that the Fe3 plus touches the wire where the electrons are coming in. The iron is being reduced here, right? Electrons are coming in, iron 3 plus hits the wire, picks up an electron to become iron 2 plus. So that's the job of the platinum. It's not participating in redox, it's just carrying electrons. Okay? So those are the things about these diagrams that you're likely to come across in a class like this. Okay? The vertical bars are for every single phase boundary, solid to aqueous, aqueous to gas, whatever. The double vertical bars are always for the salt bridge. They separate the half reactions. If we have just a conductor present, because we don't have a conductor as part of our redox, it will be listed separately. If we have multiple ions from the same element in solution together, they're separated with a comma. Oxidation on the left, reduction on the right, and we can watch the electrons flow through our diagram. Cobalt gives up 2 electrons to become cobalt 2 plus. Those 2 electrons reduce 2 iron 3 pluses to 2 iron 2 pluses. We'll get to balancing those eventually through a platinum wire. Okay? So when you see these diagrams, try not to freak out. Find the bar, find the divider. To the left must be the oxidation part, to the right must be the reduction part. So you should be able to go from a diagram like this, the line diagram, to the picture, and vice versa. All right, when we come back, we'll look at balancing a couple of these relatively simple electrochemical processes.